Before we start routing the GND, let me ask you something. Looking at the board now, if we just drop a copper port on top, it might seem like everything's done, right? But actually, there's still a hidden issue. Can you spot it? The answer is, the vias are too small for power connections. Each servo can draw up to 250 mA, and with 4 of them, that's over 1A. If your power trace only connects through a tiny via, that's definitely not enough. A single via can barely handle 1A, and that's already its limit. So even if DRC passes and everything looks clean, we still need to strengthen the GND and power connections. That means more vias, not just one. Later on, we can also add copper fills to help the high current distribute more smoothly. Especially for the VIN net, that's your battery input line. You must add 2 to 3 vias. Remember, we're taking about up to 1A current here. Relying on just one via is way too risky. One more thing, if you want to increase the via size, make sure you stick to standard drill sizes. If the via is too big, the manufacturer might change extra, or even reject your board. So stay within standard options unless you really have to customize. As for the 3.3 volt net, you don't really need to add extra vias there. Why? Because it carries very little current. All combined, it probably doesn't even hit 200 mA. So if you want to add vias, sure, go ahead. If not, no big deal, it won't affect the performance. What really matters is the 5 volt net and the VBAT line. One more thing to watch out for. Don't suddenly change your trace too drastically. Jumping from a narrow trace to a wide one can cause impedance discontinuity. That might lead to signal integrity issues like reflections or ringing. This is especially problematic with high-speed signals. Now, in our case, it's mostly power lines, so it's not super critical, but still, developing good habits is key. If you really need to change widths, do it gradually, or use a fill zone to smooth out the transition. Once you've added your vias and copper fills, run another DRC check to make sure everything is still fine. Don't forget to add teardrops while you're at it. Next, upgrade your silkscreen labels. Make sure 5V, GND, 3.3 volt are clearly marked. That really helps during soldering. If your labels are unclear, you might accidentally connect GND to 3.3 volt, and just like that, the board is fried. Same goes for TX and RX. If you swap them, serial communication won't work, the program won't upload, and you'll waste hours troubleshooting. Alright, now let's take a look at the 3D preview. Most parts may not have models, so the board might look kind of empty, but that's okay. What really matters is your layout and mechanical structure. As long as your DRC passes, silkscreen is labeled, Cooper pawls and vias are in place, you're ready to place your PCB holder. The ordering process is super simple. EasyEDA supports one-click ordering. Just go to Order and go to Order PCB, which is really easy. Upload your Gerber files to JLC PCB. The default green color is the fastest, usually shifts within a day. You can also choose red, black, or blue. But keep in mind that other colors take longer to produce. If you're just prototyping, no need to enable the PCB assembly. We're not using the option right here, just hand solder the parts yourself. If you've already finished designing your PCB, feel free to email me. I'll send you a coupon for components. I believe most of you will be able to finish the whole thing in 3 to 4 hours. With this walkthrough, plus the files and materials provided, you should be well equipped to handle it. So, what exactly happens if there's impedance discontinuity? Simply put, signal transmission gets messy. Ideally, your signals should switch cleanly, high to low, low to high. But with impedance mismatches, you'll see strange waveforms, spikes, jitter, even multiple transitions. Your oscilloscope won't show a clean square wave, instead it will be a noise and glitches. This is a big deal for high-speed signals. For power lines, it's less critical, but again, good habits matter. Avoid sudden width changes and sharp corners. Now let's talk about C4. Why did we place it right here? If you put it off to the side, far from the main current path, it basically becomes useless. Capacitors are like little water tanks. They help by supplying quick bursts of current to smooth voltage tips. But if they are placed too far from the power line, then when voltage dips happen, they can't react fast enough. So make sure your decoupling caps are placed near the load, right between power and G&D with short, direct traces. Someone asked, can I replace the LDO with an SMD version? Of course, as long as you can source and solder it. If you've got solder paste and a hot plate, go for it. In our reference design, we use through-hole parts just to make it easier for beginners to hand solder. But if you are experienced, SMD is perfectly fine. Another important point, avoid using 90-degree corners when routing traces. Think of current like water. Have you ever seen a river turn at a perfect right angle? No, because sharp corners create turbulence. In PCBs, 90-degree turns can cause signal reflection, impedance spikes, and noise. So always use rounded corners or at least 45-degree angles. Earlier, we added some teardrops. And no, they're not just for looks. They increase the connection area between traces and pads, improving both mechanical strength and conductivity. Especially useful for high current or critical connections. Someone might ask, can I skip the Cooper port and just route G&D manually? Well, technically yes, but it's very efficient. Use a ground port helps establish a common reference, which is at 0 volt, stabilizes voltage, reduces noise, and even improves thermal dissipation. So overall, copper ports are more professional and much more reliable. But remember, every time you edit your layout, you need to rebuild your copper ports. Otherwise, you might get short circuits or missed connections. Always run DRC again afterward to catch any issues. Let me repeat one last thing about silkscreen. If your labels aren't clear, your board might get wrecked. GND and 3.3 volt look similar and are often close together. Mix them up and you might fry the chip instantly. So make sure everything is labeled. GND, 3v3, TX, RX, IO pins, all of it. Clearly will save you a ton of time during soldering and debugging. Alright, that wraps up our full PCB layout process for the quadruped robot main control board. There's definitely room for improvement, but it's already good enough to get started. Try doing it self once. It might take you 3-4 hours, but with this tutorial, plus the files and resources on the website, you'll absolutely be able to complete it on your own. Now that we have all the parts ready, let's take a look at what we have here. First, this is our PCB board. We ordered it from JLC PCB. Next, these are the components we ordered. We got them from LCSC. We used the BOM file exported from EasyEDA. Some things, like the servo motor and battery holder, we bought from other websites. This servo will control the legs of the Robotdog. The battery we're using is the AA battery. Before we begin, let's get the tools ready. We'll need a soldering iron, some solder wire, and a room without a smoke alarm that might go off. Now we can start soldering. Let's start with a simple resistor. Pick the one you need, for example, a 10 ohm resistor. Check the color bands to make sure that it's the correct value. Now, insert the two legs of the resistor into the correct holes on the PCB. Bend the legs on the back a little. This will help keep the resistor in place. Wait for it to heat up. About 350 Celsius is good. Hold the soldering iron in your right hand. Hold the solder wire in your left hand. Touch the iron to where the metal leg and the pad meet. Then feed in a little bit of solder. The solder will melt and flow around the leg. After 1 or 2 seconds, move the iron away. Check the solder point. It should look shiny and smooth. Use a wire cutter to trim the extra part of the resistor leg. Be careful not to damage the solder point. Next, we will solder the ESP8266 module. We're using the ESP12F version. It has 2 rows of small pins. It's a surface mount module, a bit harder, but don't worry. Find the little antenna icon on the module. Make sure it's facing up and outward. Now align the pins with the pads on the PCB. Add a bit of solder to one pad on the board. Place the module on top, line it up carefully. Use 2 tweezers to hold it in place. Then use the soldering iron to melt that corner pad. This will hold the module so it doesn't move. Start on one side. Pin by pin, take your time. Touch the iron to where the pin meets the pad. Add a small bit of solder. Don't use too much. We don't want pins to stick together. Each pin should take only 1 to 2 seconds. Too much heat can hurt the chip. When you finish one side, check the result and look carefully. Are the joints shiny and round? Are there any pins stuck together? If needed, you can fix them using solder wick or flux. Now, flip the board and do other row of pins in the same way. And that's it. All the parts are soldered and the module is firmly in place. This is what your circuit board should look like when it's done.